You're standing in your backyard on a clear night, gazing up at the star-filled cosmos above. Those distant suns have been shining for billions of years, their light traveling unimaginable distances to reach your eyes. But what if I told you that sometimes those distant stellar neighborhoods send us more than just light? What if they dispatch actual messengers, ancient wanderers that have journeyed across the vast emptiness between stars to pay our solar system a visit? Welcome to the extraordinary story of 3i Atlas, a cosmic nomad that has captivated astronomers worldwide and challenged everything we thought we knew about our place in the galaxy. This isn't just another space rock drifting through our celestial neighborhood. This is something far more remarkable, a genuine visitor from the stars that has traveled distances so vast they defy human comprehension, carrying secrets from worlds we can barely imagine. The tale begins with a discovery that sent shockwaves through the astronomical community. On a seemingly ordinary night, telescopes around the world turned their mechanical eyes skyward and spotted something that shouldn't have been there. Something moving in a way that defied the gravitational rules of our solar system. Something that was clearly, undeniably, not from here. 3i Atlas represents only the third confirmed interstellar object ever detected passing through our solar system, making it rarer than the most precious diamonds on Earth. To put this in perspective, imagine finding only 3 grains of sand from a distant beach scattered across an entire continent. That's how extraordinary these interstellar visitors truly are. The designation 3i might sound like scientific jargon, but it carries profound meaning. The I stands for interstellar, marking this object as a confirmed traveler from beyond our sun's gravitational domain. The number 3 indicates its position in the exclusive club of interstellar objects we've managed to detect and track. Only 3 confirmed members exist in this cosmic registry, making 3i Atlas a celebrity among celestial bodies. But what makes an object interstellar? The answer lies in the fundamental physics of orbital mechanics and the invisible boundaries that define our solar system's sphere of influence. Every object naturally bound to our sun follows an elliptical path, forever trapped in its gravitational embrace. These bound objects might venture far from the sun, but they always return, like cosmic boomerangs drawn back by invisible forces. 3i Atlas, however, follows a completely different set of rules. Its trajectory forms what astronomers call a hyperbolic orbit, a mathematical curve that spells freedom from solar gravity. Unlike the closed loops traced by planets and comets, a hyperbolic path is open-ended, stretching to infinity. Objects following such trajectories arrive from the depths of space, swing around our sun once, and then depart forever, never to return. This hyperbolic signature became the smoking gun that proved 3i Atlas originated elsewhere in the galaxy. When astronomers first calculated its orbital elements, the numbers told an unmistakable story. The object's velocity exceeded the sun's escape velocity at its current distance, meaning it possessed enough kinetic energy to break free from our star's gravitational chains entirely. The discovery process itself reads like a detective story. Ground-based telescopes initially spotted 3i Atlas as nothing more than a faint moving dot against the star-filled background. Those first observations revealed unusual motion patterns that immediately caught the attention of asteroid hunters and comet specialists. Night after night, astronomers tracked its position, building up a database of measurements that would eventually reveal its true nature. As more observations accumulated, the picture became increasingly clear and increasingly extraordinary. The object's trajectory, when projected backward in time, originated from a region of space far beyond the boundaries of our solar system. When projected forward, it showed 3i Atlas departing our cosmic neighborhood permanently, bound for the empty spaces between stars. The realization that they were witnessing an authentic interstellar visitor triggered an unprecedented observational campaign. Telescopes around the world swiveled to track this cosmic wanderer, from massive ground-based instruments to sophisticated space observatories. Every photon of light reflected from 3i Atlas became precious scientific data, a messenger carrying information about distant stellar systems. But tracking an interstellar object presents unique challenges that don't apply to local solar system bodies. These visitors move incredibly fast relative to Earth, their apparent motion across the sky changing rapidly as they race through our neighborhood. Unlike asteroids or comets that astronomers can study for months or years, interstellar objects offer only brief windows of opportunity before disappearing back into the cosmic void. The speed of 3I Atlas relative to our Sun measures approximately 11 kilometers per second, a velocity that seems modest until you consider the context. This represents the object's excess velocity, the speed remaining after accounting for the Sun's gravitational acceleration. In other words, even after our star's gravity pulled 3I Atlas toward it, accelerating it to tremendous speeds, it still retained enough velocity to escape permanently. To put this cosmic velocity in perspective, 11 kilometers per second equals nearly 25,000 miles per hour. At this speed, 3I Atlas could traverse the entire width of the United States in less than 10 minutes. Such tremendous velocity speaks to the object's interstellar origins and the vast distances it has traveled to reach our solar system. The gravitational dynamics governing 3I Atlas's journey reveal fascinating details about its cosmic voyage. As the object approached our solar system from interstellar space, it encountered the Sun's gravitational field gradually. This invisible force began accelerating 3I Atlas long before it became detectable by our telescopes, pulling it into an increasingly curved trajectory. The closest approach to our Sun, known as perihelion, represented the climactic moment of 3I Atlas's solar system visit. At this point, traveling at maximum velocity, the object experienced the full intensity of solar radiation and gravitational forces. The Sun's gravity bent its trajectory into the characteristic hyperbolic curve, redirecting 3I Atlas toward its ultimate exit from our cosmic neighborhood. Understanding the orbital mechanics of 3I Atlas requires grappling with concepts that challenge human intuition. In the vacuum of space, objects continue moving in straight lines unless acted upon by external forces. The Sun's gravity provides that external force, continuously pulling 3I Atlas toward our star, while the object's tremendous velocity carries it past the Sun rather than into it. This cosmic dance between gravity and velocity creates the hyperbolic trajectory that marks 3I Atlas as an interstellar visitor. The mathematical equations describing this orbital path contain encoded information about the object's origins, revealing clues about its journey through galactic space and its eventual destination among the stars. The hyperbolic nature of 3I Atlas's orbit also determines its visibility window from Earth. Unlike periodic comets that return predictably every few years or decades, interstellar visitors offer only a single observational opportunity. Once 3I Atlas departs our solar system, it will never return, making every observation precious and irreplaceable. This fleeting nature of interstellar objects explains why so few have been detected throughout human history. Before the development of modern astronomical surveys and automated sky monitoring systems, such fast-moving visitors likely passed through our solar system unnoticed, invisible messengers from distant stars that came and went without leaving any record of their passage. The technological revolution in astronomy over the past few decades has finally given us the tools necessary to detect and track these cosmic wanderers. Sophisticated computer algorithms scan millions of star images nightly, searching for the telltale motion signatures that betray moving objects against the stellar background. These automated systems can process vast amounts of data far faster than human observers, catching interstellar visitors that would otherwise remain invisible. 3I Atlas owes its discovery to the Atlas Survey System, a network of telescopes designed specifically to detect potentially hazardous asteroids that might threaten Earth. The name Atlas stands for Asteroid Terrestrial Impact Last Alert System, reflecting its primary mission of planetary defense. However, this asteroid hunting network has proven equally capable of discovering much more exotic objects, including genuine visitors from other star systems. The Atlas telescopes use wide-field cameras to photograph large sections of sky multiple times per night, creating a continuous movie of celestial motion. computer algorithms analyze these images, identifying objects that move between successive frames. Most detections turn out to be routine asteroids or comets, but occasionally the system captures something truly extraordinary. When Atlas first detected 3I Atlas, the object appeared as nothing more than a faint streak of light moving against the stellar background. Initial classifications suggested it might be another near-Earth asteroid, one of thousands discovered annually by various sky surveys. Only subsequent observations and detailed orbital calculations revealed its true interstellar nature. The confirmation process for interstellar objects requires extensive follow-up observations and careful analysis. Astronomers must rule out all possible solar system origins before declaring an object genuinely interstellar. This involves calculating precise orbital trajectories, accounting for gravitational perturbations from major planets, and verifying that no known mechanism could produce the observed hyperbolic orbit within our solar system. The mathematical techniques used to determine 3I Atlas's interstellar status rely on centuries of celestial mechanics development. From Newton's laws of gravitation to modern computational methods, every position measurement contributes to refining the orbital solution, gradually building confidence in the object's extrasolar origins. The process resembles assembling a cosmic jigsaw puzzle, with each observational data point providing another piece of the complete picture. Early observations might suggest several possible orbital solutions, but additional measurements progressively eliminate alternatives until only the interstellar interpretation remains consistent with all available evidence. This rigorous verification process explains why astronomers exercise such caution before confirming interstellar objects. The implications of such discoveries are profound, representing our first direct samples of material from other stellar systems. False identifications would undermine scientific credibility and potentially misdirect research efforts, making thorough verification essential. The confirmation of 3I Atlas as a genuine interstellar visitor marked a significant milestone in astronomical history. Only two previous objects, 1I Oumuamua and 2I Borisov, had received confirmed interstellar designations, making 3I Atlas part of an extremely exclusive cosmic club. Each confirmed interstellar object has contributed unique insights into the nature of material wandering between stars. 1I Oumuamua, the first discovered interstellar visitor, appeared as an elongated rocky body with unusual acceleration characteristics that continue to puzzle scientists. 2I Borisov resembled a more traditional comet, complete with a visible tail of sublimating ices and dust. 3I Atlas adds another chapter to this emerging story of interstellar objects, providing additional data points for understanding the population of material drifting through galactic space. Every confirmed interstellar visitor helps astronomers refine their models of planetary system formation and the processes that eject material into interstellar space. The rarity of confirmed interstellar objects reflects both their genuine scarcity and the observational challenges involved in detecting them. These visitors move rapidly across Earth's sky, often becoming visible only when they approach relatively close to our Sun. The combination of high velocity and typically small size makes them extremely difficult targets for ground-based telescopes. Most interstellar objects likely pass through our solar system undetected, invisible to current survey systems due to their faintness or unfortunate timing. Astronomers estimate that several interstellar visitors transit our cosmic neighborhood annually, but most remain beyond the detection limits of existing telescopes. The detection rate for interstellar objects should increase dramatically as new survey systems come online and existing telescopes receive sensitivity upgrades. Projects like the Vera Rubin Observatory, scheduled to begin operations soon, will photograph the entire visible sky every few nights with unprecedented depth and precision. This next generation of sky surveys promises to revolutionize interstellar object science, potentially discovering dozens or hundreds of cosmic visitors annually, instead of the current rate of roughly one per year. Such increased detection rates will enable statistical studies of interstellar object populations, revealing patterns and characteristics invisible in today's small sample size. The physical properties of 3I Atlas remain shrouded in observational uncertainty, reflecting the inherent challenges of studying objects millions of kilometers away that reflect only tiny amounts of sunlight. Determining basic characteristics like size, shape, rotation period, and surface composition requires sophisticated analysis techniques and often yields results with substantial error margins. Size estimation represents one of the most fundamental yet challenging aspects of interstellar object characterization. Astronomers measure an object's apparent brightness, but converting this brightness measurement into physical size requires assumptions about surface reflectivity, or albedo. Dark objects appear smaller than they actually are, while highly reflective surfaces can make small objects appear deceptively large. For 3I Atlas, size estimates range from hundreds of meters to several kilometers in diameter, an uncertainty span that encompasses objects differing in volume by factors of thousands. This enormous uncertainty reflects both the object's distance from Earth during observations and the unknown properties of its surface materials. The albedo assumption proves particularly problematic for interstellar objects, which may possess surface compositions completely unlike anything found in our solar system. Material that formed around different stars, under different conditions, might exhibit reflective properties that confound size estimates based on local solar system experience. Spectroscopic observations, which analyze the wavelengths of light reflected from 3I Atlas, provide additional clues about its composition and physical properties. Different materials absorb and reflect specific wavelengths in characteristic patterns, creating spectroscopic fingerprints that reveal chemical composition. However, obtaining high-quality spectra of rapidly moving, faint interstellar objects challenges even the most sophisticated telescopes. The limited photon flux requires long exposure times, but the object's rapid motion across the sky constrains how long telescopes can track it effectively. This creates a fundamental tension between the time needed to collect sufficient light and the object's observable window. The spectroscopic data available for 3I Atlas suggests a composition broadly similar to outer solar system comets, with signatures indicating the presence of water ice, carbon-bearing compounds, and silicate minerals. However, these measurements come with substantial uncertainties, and more exotic compositions cannot be definitively ruled out. The presence of water ice in 3I Atlas provides important clues about its formation environment. Water represents one of the most abundant molecules in the universe, condensing from gas into solid ice at temperatures below approximately -160 degrees Celsius. The preservation of water ice in 3I Atlas indicates that the object formed in the cold outer regions of some planetary system, far from the warmth of its parent star. Carbon-bearing compounds, or organics, represent another significant component suggested by spectroscopic analysis. These complex molecules form through various processes in the cold environments of outer planetary systems, where carbon monoxide, methane, and other simple molecules can undergo chemical reactions to produce more complex organic species. The detection of organic compounds in interstellar objects carries profound implications for astrobiology, the study of life's potential throughout the universe. These molecules represent the chemical building blocks from which life emerges, and their presence in material from other star systems demonstrates that the raw ingredients for biology exist throughout the galaxy. Silicate minerals, the rocky components suggested in 3I Atlas's spectrum, provide information about the object's formation in a protoplanetary disk around a young star. These minerals condense from hot gas close to stars and become incorporated into planetesimals, the building blocks of rocky planets and asteroids. The combination of ices, organics, and silicates in 3I Atlas paints a picture of an object that formed in the outer regions of an alien planetary system, where temperatures remained cold enough to preserve volatile compounds while still incorporating rocky material from the inner disk regions. This compositional profile resembles that of long-period comets in our own solar system, suggesting that 3I Atlas might represent ejected material from the outer regions of another star's planetary system. Such ejection could result from gravitational interactions with giant planets, stellar encounters, or other dynamic processes that occasionally fling material into interstellar space. The age of 3I Atlas remains one of its most intriguing and poorly constrained properties. Unlike solar system objects whose ages can be estimated through various dating techniques, interstellar visitors carry no clear chronological markers that reveal their formation times or journey durations. Theoretical models suggest that objects like 3I Atlas could be extremely ancient, possibly billions of years old. If ejected from their parent stellar systems during early planetary formation epochs, these wanderers might have been drifting through galactic space for substantial fractions of the galaxy's total age. The Milky Way galaxy itself formed approximately 13 billion years ago, and star formation has continued throughout its history. 3I Atlas could potentially date back to any period in this vast timeline, from relatively recent ejection events to primordial material expelled during the galaxy's earliest epochs of stellar birth. The concept of such ancient cosmic wanderers challenges human temporal intuition. An object billions of years old would predate the formation of our own solar system by substantial margins. Such visitors carry information about stellar systems that formed, evolved, and possibly died long before our sun began to shine. Space weathering processes gradually modify the surfaces of objects exposed to cosmic radiation, solar wind, and micrometeorite bombardment over geological timescales. The extent of such weathering on 3I Atlas might provide clues about its exposure age, the time spent in the harsh environment of interstellar space. However, interpreting space weathering signatures requires understanding the specific processes that affect objects in the interstellar medium, an environment quite different from the inner solar system where most space weathering studies have been conducted. The lower density of particles and radiation in interstellar space might produce weathering patterns unlike anything observed on solar system bodies. The journey of 3I Atlas through our solar system provides a unique opportunity to study an authentic sample of interstellar material without the enormous expense and technological challenges of launching interstellar space missions. This visitor effectively delivers itself to our cosmic doorstep, offering scientists a chance to analyze genuine extrasolar material using ground-based and space-based telescopes. The trajectory of 3I Atlas through our planetary system can be reconstructed through careful analysis of its gravitational interactions with major bodies. As the object approached from interstellar space, it first encountered the gravitational influence of the outer gas giant planets, whose massive gravitational fields began subtly altering its trajectory long before it became detectable. Jupiter, with its enormous mass and extensive gravitational sphere of influence, likely provided the first significant perturbation to 3I Atlas's incoming trajectory. Although the object passed well outside Jupiter's orbit, the planet's gravitational field would have imparted small but measurable changes to the visitor's velocity and direction. Saturn, Uranus, and Neptune each contributed additional gravitational modifications as 3I Atlas continued its inward journey toward the Sun. These perturbations, while individually small, collectively influenced the object's final trajectory and timing of perihelion passage. The gravitational influence of Mars became significant as the 3I Atlas passed through the inner solar system. The red planet's gravity provided another small but detectable modification to the object's path, contributing to the complex dance of gravitational forces that determined the visitor's exact trajectory. Earth's gravitational field also affected 3I Atlas, despite the object passing at a considerable distance from our planet. This interaction provided astronomers with additional data points for refining orbital calculations and verifying the object's interstellar nature. The Moon's gravity, while much weaker than Earth's, still contributed measurable perturbations to 3I Atlas's trajectory. These subtle effects demonstrate the remarkable precision required in calculating interstellar object orbits, where even relatively minor gravitational influences must be accounted for in detailed trajectory models. As 3I Atlas approached its closest solar encounter, the Sun's intense gravitational field dominated all other influences. The enormous acceleration imparted by solar gravity reached its maximum at perihelion, when the object experienced the full intensity of our star's gravitational attraction. The perihelion passage represents the most energetic phase of 3I Atlas's solar system visit. At this point, the object reached its maximum velocity relative to the Sun, racing past our star at speeds approaching the limits of gravitational acceleration. The intense solar radiation and particle bombardment at perihelion likely triggered significant changes in the object's surface properties and possibly its internal structure. Solar heating during perihelion passage could have sublimated surface ices, creating temporary coma and tail features similar to those observed in traditional comets. However, detecting such activity in rapidly moving interstellar objects requires extremely sensitive observations and often proves challenging given the brief observational windows available. The thermal effects of solar heating penetrate only shallow depths into solid objects, meaning that most of 3I Atlas's interior likely remained unaffected by its solar system passage. The bulk of the object probably preserves pristine material from its original formation environment, carrying chemical and isotopic signatures of its parent stellar system. Following perihelion passage, 3I Atlas began its permanent departure from our solar system. The Sun's gravity, which had accelerated the object inward, now worked to slow its recession, but the visitor's hyperbolic trajectory ensured that it would eventually escape entirely. The outbound journey of 3I Atlas reverses the gravitational interactions experienced during its approach. Each planetary encounter now occurs in reverse order, with the gas giants providing final small perturbations as the object heads toward interstellar space. The transition from solar system resident to interstellar traveler occurs gradually as 3I Atlas moves beyond the gravitational dominance of our Sun. At increasingly large distances, the solar gravitational field weakens, eventually becoming negligible compared to the gravitational influences of nearby stars. The heliopause, the boundary where the solar wind gives way to the interstellar medium, represents a symbolic milestone in 3I Atlas's departure. Beyond this boundary, the object truly returns to interstellar space, beginning a new chapter in its cosmic wandering that may continue for millions or billions of years. The ultimate destination of 3I Atlas remains uncertain, governed by the complex gravitational environment of our local galactic neighborhood. Nearby stars will gradually influence its trajectory, potentially redirecting the object toward different regions of the galaxy, or even capturing it into a new stellar system. Computer simulations can project the future path of 3I Atlas for limited periods, but the chaotic nature of gravitational dynamics in multi-body systems makes long-term predictions increasingly uncertain. Small perturbations accumulate over time, eventually making precise trajectory forecasts impossible beyond certain time horizons. The study of 3I Atlas's chemical composition reveals fascinating insights into planetary formation processes around other stars. The specific mix of materials detected in this interstellar visitor provides clues about the temperature, pressure, and chemical conditions present in its birth environment billions of years ago. Water ice, one of the primary components suggested by spectroscopic analysis, forms through relatively straightforward chemical processes in the cold outer regions of protoplanetary disks. The hydrogen and oxygen that combine to create water represent two of the most abundant elements in the universe, making water ice a common constituent of objects forming beyond the frost line around young stars. The preservation of water ice in 3I Atlas indicates that the object formed far enough from its parent star to remain below the sublimation temperature throughout its initial evolution. This suggests an origin in the outer reaches of an alien planetary system, in regions analogous to the Kuiper Belt or Oort cloud in our own solar system. Carbon monoxide ice, another possible component of 3I Atlas, requires even colder formation temperatures than water ice. The detection of carbon monoxide would indicate formation in the most distant frigid regions of a protoplanetary disk, where temperatures dropped below -200 degrees Celsius. Methane ice represents another potential constituent that forms only in extremely cold environments. The presence of methane would suggest that 3I Atlas originated in regions comparable to the outer reaches of our own solar system, where objects like Pluto and other dwarf planets show methane signatures. The organic compounds potentially detected in 3I Atlas's spectrum represent more complex chemical species that form through various processes in protoplanetary disk environments. These molecules might result from radiation-driven chemistry, thermal processing, or other mechanisms that create organic complexity from simpler starting materials. Amino acids, the building blocks of proteins essential to life as we know it, could potentially exist within the organic inventory of 3I Atlas. While current observational techniques cannot detect such specific molecules, laboratory analysis of returned samples from similar objects might reveal a rich organic chemistry relevant to astrobiology. The silicate minerals suggested in 3I Atlas's composition provide information about high-temperature processes in its parent protoplanetary disk. These rocky components form close to young stars, where temperatures reach hundreds or thousands of degrees, hot enough to condense refractory materials from gas phase. The presence of both high-temperature silicates and low-temperature ices in a single object suggests complex formation and evolution processes. 3I Atlas might have assembled through accretion of materials from different regions of its parent protoplanetary disk, collecting both hot inner zone minerals and cold outer zone ices during its growth. Alternatively, the object might have formed in the cold outer regions and subsequently acquired silicate components through collisions with rocky debris, impacts from meteoroids, or other mixing processes that combined materials of diverse thermal histories. The isotopic ratios of elements in 3I Atlas, if measurable with sufficient precision, could provide crucial clues about its formation environment. Different stars produce characteristic isotopic signatures through nuclear processes, and these signatures become incorporated into the materials forming in their protoplanetary disks. Oxygen isotope ratios, for example, vary significantly between different stellar environments depending on the nuclear processes that occurred in previous generations of stars. Measuring these ratios in 3I Atlas could potentially identify the type of star around which it formed, or even constrain the timing of its formation relative to galactic chemical evolution. Carbon isotope ratios provide another potential diagnostic tool for understanding 3I Atlas's origins. The ratio of carbon-12 to carbon-13 reflects the nuclear processes and chemical evolution history of the stellar environment where the object formed. Nitrogen isotopes carry information about the chemical conditions and evolutionary state of the protoplanetary disk environment. These measurements could reveal whether 3I Atlas formed in a disk around a young star rich in heavy elements or an older star with different chemical abundances. The challenge of measuring isotopic ratios in distant faint objects like 3I Atlas pushes current observational techniques to their limits. Such measurements typically require high-resolution spectroscopy with extremely sensitive instruments and long exposure times that may exceed the observational windows available for rapidly moving interstellar objects. Future technological developments in spectroscopic instrumentation may eventually enable detailed isotopic analysis of interstellar visitors. Advanced ground-based telescopes and space-based observatories could provide the sensitivity and spectral resolution necessary to unlock the chemical secrets carried by these cosmic wanderers. The rotation of 3I Atlas provides another observable property that constrains models of its physical structure and formation history. Objects acquire rotational angular momentum through various processes during formation and evolution, and measuring rotation rates can reveal information about internal mass distribution and collisional history. Determining rotation periods for distant faint objects requires detecting brightness variations as different surface regions alternately face toward and away from Earth. These light curve measurements demand precise photometry over extended time periods, challenging observational resources and weather conditions. The rotation period of 3I Atlas, if successfully measured, could indicate whether the object represents a single coherent body or a loosely bound aggregate of smaller components. Rapidly rotating objects must possess sufficient internal strength to resist centrifugal disruption, while slowly rotating bodies might consist of weakly bound material held together primarily by gravity. Contact binary objects, which consist of two roughly spherical components in gentle contact, represent one possible configuration for 3I Atlas. Such objects form through low-velocity collisions between similar-sized bodies and exhibit characteristic light curve signatures that reveal their binary nature. Rubble pile structures, consisting of numerous smaller fragments held together by weak gravitational attraction, represent another possible internal configuration. These objects can exhibit complex rotation behaviors and irregular shapes that produce distinctive observational signatures. The surface properties of 3I Atlas remain poorly constrained due to observational limitations, but theoretical models suggest various possibilities based on the harsh environment of interstellar space. Cosmic ray bombardment over millions or billions of years could have significantly altered surface chemistry and physical properties. Space weathering in the interstellar medium differs substantially from similar processes in the inner solar system. The lower density of particles and radiation in interstellar space might produce different weathering patterns than those observed on solar system objects. Micrometeorite bombardment represents another surface modification process that could affect 3I Atlas during its interstellar journey. Although the density of solid particles in interstellar space remains extremely low, high relative velocities could produce significant impact effects over geological timescales. The color of 3I Atlas provides clues about its surface composition and weathering history. Photometric observations in multiple wavelength bands can reveal the object's spectral reflectance properties, which correlate with surface mineralogy and organic content. Reddish coloration often indicates the presence of organic compounds that have undergone radiation processing or thermal alteration. Many outer solar system objects exhibit red colors attributed to organic materials called tholins, complex polymers created through radiation chemistry. Neutral or grayish colors might suggest surfaces dominated by silicate minerals or primitive carbonaceous materials. Such coloration would be consistent with objects formed in the outer regions of protoplanetary disks, where organic processing remains limited. The albedo, or reflectivity of 3I Atlas, constrains both its size and surface properties. Higher albedo values indicate more reflective surfaces composed of materials like water, ice, or bright silicates, while lower values suggest darker surfaces rich in organic compounds or metallic materials. Measuring accurate albedo values requires simultaneous determination of an object's size through independent techniques such as thermal infrared observations. The thermal emission from 3I Atlas depends on its temperature, which in turn depends on its distance from the Sun and surface thermal properties. The thermal inertia of 3I Atlas's surface affects how quickly it responds to changing solar illumination as the object moves through its trajectory. Low thermal inertia suggests loose, insulating surface materials, while high values indicate more consolidated or conductive surfaces. The study of 3I Atlas contributes to our broader understanding of interstellar object populations and the processes that create these cosmic wanderers. Each confirmed interstellar visitor provides additional data points for statistical analysis of their physical and orbital characteristics. Population synthesis models attempt to predict the number and properties of interstellar objects based on theoretical understanding of planetary system formation and evolution. These models must account for the various dynamical processes that can eject material from planetary systems into interstellar space. Gravitational interactions with giant planets represent one of the primary ejection mechanisms for creating interstellar objects. As these massive planets migrate through their systems during formation, they scatter smaller bodies, occasionally imparting enough energy to achieve escape velocity. Stellar encounters with neighboring stars can also disrupt planetary systems, ejecting material into interstellar space. Such encounters become more likely in dense stellar environments like young star clusters, where multiple star systems exist in close proximity. Supernova explosions represent extreme events that can completely disrupt planetary systems, launching all their constituent material into interstellar space at high velocities. Objects ejected by such violent processes might exhibit unusual compositions or physical properties that distinguish them from more gently ejected material. The galactic environment influences the production and transport of interstellar objects through various mechanisms. Regions of active star formation create more opportunities for planetary system disruption and material ejection, while older, more stable stellar populations contribute fewer interstellar wanderers. Gravitational focusing by massive objects like stellar clusters or molecular clouds can concentrate interstellar objects along certain trajectories, creating preferential directions from which these visitors approach our solar system. Understanding these focusing effects helps astronomers predict where future interstellar objects might be discovered. The velocity distribution of interstellar objects carries information about their ejection mechanisms and galactic environment. Objects ejected by gentle planetary interactions exhibit different velocity signatures than those launched by violent stellar encounters or supernova explosions. Measuring the chemical composition of multiple interstellar objects enables comparative studies that reveal patterns related to stellar metallicity, age, and formation environment. Such comparisons might eventually allow astronomers to trace interstellar visitors back to their origins in different stellar populations. The discovery rate of interstellar objects provides constraints on theoretical models of their production mechanisms. Current detection rates suggest that substantial populations of these objects exist throughout the galaxy, but observational selection effects make it difficult to determine their true space density. As observational capabilities improve, astronomers expect to discover many more interstellar objects, enabling statistical studies impossible with today's small sample sizes. These future discoveries will test theoretical predictions and refine our understanding of planetary system evolution throughout the galaxy. The legacy of 3I Atlas extends beyond its specific physical properties to encompass broader questions about our place in the cosmic environment. This visitor demonstrates that our solar system exists within a galactic ecosystem where material regularly exchanges between stellar systems. The detection of organic compounds in interstellar objects like 3I Atlas has profound implications for astrobiology and the potential for life throughout the galaxy. These objects might serve as vectors for transporting organic molecules and even potentially viable organisms between star systems. Panspermia theories suggest that life might spread throughout the galaxy via interstellar objects carrying biological material from one planetary system to another. While highly speculative, the discovery of organic-rich interstellar visitors like 3I Atlas provides some observational context for evaluating such possibilities. The preservation of complex organic molecules in the harsh environment of interstellar space requires understanding the chemical and physical processes that might protect biological materials during million-year journeys between stars. Radiation shielding, low temperatures, and other factors could potentially maintain molecular integrity over such timescales. Laboratory experiments simulating interstellar conditions have demonstrated that certain organic compounds and even some simple biological structures can survive exposure to cosmic radiation, extreme temperatures, and vacuum conditions for extended periods. These results suggest that interstellar transport of organic material remains at least theoretically possible. The study of 3I Atlas also contributes to planetary defense efforts by improving our understanding of potentially hazardous objects that might approach Earth. While interstellar visitors like 3I Atlas pose no immediate threat due to their hyperbolic trajectories, understanding their properties helps astronomers distinguish between genuine threats and harmless passers-by. Impact risk assessment requires accurate determination of object size, composition, and trajectory. The techniques developed for studying 3I Atlas contribute to the broader toolkit available for characterizing potentially hazardous asteroids and comets that might threaten Earth. The observational challenges encountered in studying 3I Atlas have driven technological developments in telescope instrumentation, data analysis techniques, and orbital determination methods. These advances benefit the broader field of solar system astronomy and contribute to improved capabilities for detecting and tracking various types of celestial objects. Automated survey systems, like those that discovered 3I Atlas, represent the future of solar system exploration, capable of monitoring vast regions of sky with unprecedented sensitivity and temporal coverage. These systems will undoubtedly discover many more interstellar objects in the coming years and decades. Machine learning algorithms increasingly play crucial roles in identifying and classifying celestial objects detected by automated surveys. The development of sophisticated pattern recognition software enables rapid processing of enormous datasets, identifying interesting objects that warrant follow-up observations. The international collaboration required to study objects like 3I Atlas demonstrates the global nature of modern astronomy. Telescopes around the world contribute observations, while researchers from multiple institutions collaborate on data analysis and interpretation. Space-based base observatories provide unique capabilities for studying interstellar objects, offering uninterrupted observations free from atmospheric interference. The Hubble Space Telescope, Spitzer Space Telescope, and other orbital observatories have contributed valuable data on interstellar visitors. Future space missions might eventually target interstellar objects for close-up study, launching spacecraft to intercept these visitors during their solar system passages. Such missions would provide unprecedented detail about interstellar object properties and composition. The technical challenges of intercepting rapidly moving interstellar objects with spacecraft require innovative mission design and propulsion technologies. The brief notice typically available for interstellar object discoveries makes pre-planned missions extremely difficult, demanding rapid response capabilities. Breakthrough Starshot and similar projects propose using light sails and powerful lasers to accelerate tiny spacecraft to enormous velocities capable of intercepting interstellar objects or even reaching nearby star systems. Such technologies might eventually enable detailed exploration of interstellar space. The philosophical implications of discovering authentic visitors from other star systems extend beyond scientific curiosity to fundamental questions about cosmic connectivity and our place in the galactic community. 3I Atlas represents tangible evidence that our solar system participates in a larger galactic ecosystem. The materials comprising 3I Atlas formed around another star, possibly orbited by planets, hosting environments completely different from anything found in our solar system. This visitor carries physical samples from alien worlds we may never be able to visit directly. Calibration standards for the diverse array of instruments used to observe interstellar objects ensure that measurements from different telescopes and detectors can be meaningfully compared and combined. Cross-calibration efforts identify and correct systematic biases between different observational systems. The economic impact of interstellar object research includes both direct costs of observational campaigns and indirect benefits from technological advancement and public engagement. The investment in studying these rare visitors generates returns through improved scientific understanding and technological capabilities. Cost-benefit analyses of interstellar object research must account for the unique scientific value of these observations, which cannot be replicated through any other means. The information content of each interstellar visitor justifies significant investment in comprehensive characterization efforts. Funding agencies increasingly recognize the high scientific priority of interstellar object research, despite the unpredictable timing and resource requirements associated with these discoveries. Flexible funding mechanisms enable rapid response to new discoveries while maintaining support for long-term research programs. The commercial space industry contributes growing capabilities for interstellar object research through advanced sensor systems, rapid deployment options, and cost-effective access to space-based observational platforms. Private sector involvement accelerates technological development and reduces research costs. Asteroid mining companies maintain particular interest in interstellar objects as potential sources of rare materials or as technological challenges that advance their operational capabilities. The extreme accessibility requirements of interstellar objects provide testing grounds for advanced propulsion and navigation systems. The insurance and risk assessment industries analyze interstellar objects as potential hazards to spacecraft and satellite operations, though the extremely low probability of collisions makes such risks negligible compared to conventional space debris concerns. Patent applications related to interstellar object research technologies protect intellectual property while promoting innovation in detection systems, analysis techniques, and potential intercept mission technologies. Such protection encourages private investment in research and development efforts. The legal framework governing interstellar objects remains largely undefined, with questions about property rights, scientific access, and planetary protection protocols requiring international cooperation and treaty development. These objects challenge existing space law frameworks developed for solar system bodies. Sample return missions to interstellar objects would face complex legal questions about ownership and distribution of return materials, particularly if such samples contain evidence of extraterrestrial life or technologically significant materials. International space law treaties must evolve to address the unique characteristics and scientific importance of interstellar objects, ensuring that their study benefits all humanity while preventing potential conflicts over access rights. The comparative analysis of 3I Atlas with previous interstellar visitors reveals both similarities and differences that inform our understanding of the broader population of objects wandering between stars. Each discovery adds valuable constraints to theoretical models of interstellar object properties. 1. Oumuamua's legacy includes establishing the observational and analytical framework for studying interstellar objects, despite its unusual characteristics that continue to challenge conventional explanations. The lessons learned from Oumuamua observations directly benefit studies of subsequent interstellar visitors. The size distribution of confirmed interstellar objects spans several orders of magnitude, from Oumuamua's estimated dimensions of hundreds of meters to potentially much larger objects that might eventually be discovered. This size range reflects the diverse population of small bodies in planetary systems throughout the galaxy. Shape diversity among interstellar objects appears substantial, ranging from Oumuamua's extreme elongation to the more conventional proportions suggested for 3I Atlas and 2I Borisov. This geometric variety probably results from different formation and collisional histories. Compositional differences between interstellar objects provide insights into the chemical diversity of planetary systems around different types of stars. The ice-rich composition of Borisov contrasts with the more enigmatic properties of Oumuamua, while 3I Atlas appears intermediate between these extremes. Activity levels vary dramatically among interstellar visitors, from Borisov's obvious cometary behavior to Oumuamua's apparent inactivity and 3I Atlas's more subtle characteristics. These differences reflect varying volatile content and thermal evolution during solar system passage. Trajectory analysis reveals that interstellar objects approach our solar system from different directions in space, suggesting diverse origins within the local galactic environment. The distribution of approach directions provides constraints on the spatial distribution of interstellar object populations. Velocity distributions among confirmed interstellar objects reflect their different ejection mechanisms and subsequent galactic orbital evolution. Objects ejected by gentle planetary interactions exhibit different velocity characteristics than those launched by violent stellar encounters. The detection efficiency for interstellar objects varies significantly depending on their approach, geometry, brightness, and timing relative to survey operations. Statistical corrections for these observational biases become essential for deriving true population characteristics from observed samples. Follow-up observation strategies have evolved significantly since the discovery of Oumuamua, with improved coordination between discovery surveys and characterization telescopes, enabling more comprehensive data collection within the limited visibility windows available. Theoretical modeling capabilities continue to advance through improved computational methods and better understanding of the physical processes affecting interstellar objects during their formation, evolution, and solar system passage. The future discovery rate of interstellar objects should increase substantially as next-generation survey systems begin operations, potentially revealing dozens or hundreds of these visitors annually instead of the current rate of roughly one per year. Population synthesis models predict that improved detection capabilities will reveal significant diversity in interstellar object properties, confirming that the first few discoveries represent only a small sample of the total population wandering through galactic space. the observational selection effects that currently limit interstellar object discoveries to the brightest, most accessible examples will diminish as survey sensitivity improves, revealing smaller, fainter, and more distant visitors that represent the bulk of the interstellar population. Machine learning algorithms trained on the growing dataset of interstellar object properties will enable automated classification and characterization of future discoveries, reducing the time required for confirming interstellar origins and beginning detailed studies. Real-time alert systems connecting discovery surveys with follow-up telescopes around the world will maximize the scientific return from each interstellar visitor by coordinating observations during the brief windows when these objects remain accessible to Earth-based instruments. The atmospheric and space-based telescope resources dedicated to interstellar object research continue expanding as the scientific community recognizes their unique value for understanding planetary system formation and galactic evolution processes. Spectroscopic databases compiled from multiple interstellar object observations will enable comparative studies that reveal systematic patterns in composition, structure, and behavior that remain invisible when studying individual objects in isolation. The chemical evolution of interstellar objects during their passage through different galactic environments represents an active area of theoretical research that seeks to understand how prolonged exposure to cosmic radiation and interstellar material affects their properties. Galactic chemical evolution models use interstellar objects as probes of nucleosynthesis products from different stellar populations, potentially revealing the chemical history of regions where these objects formed billions of years ago. The dynamics of interstellar object trajectories through the galaxy provide information about the gravitational potential and dark matter distribution in our local cosmic environment, contributing to understanding the structure and evolution of the Milky Way. Stellar encounter frequencies and their effects on planetary system stability can be constrained through statistical analysis of interstellar object ejection rates and velocity distributions, improving models of how planetary systems evolve over cosmic time. The survival rates of different types of materials during interstellar transport inform models of how complex molecules and potentially biological materials might spread between stellar systems, with implications for understanding the galactic distribution of life. Laboratory simulation experiments that reproduce the extreme conditions of interstellar space help interpret observations of 3I Atlas and other interstellar visitors by providing controlled studies of material behavior under relevant environmental conditions. Cosmic ray irradiation experiments using particle accelerators reveal how prolonged radiation exposure affects the chemistry and structure of materials similar to those expected in interstellar objects, enabling better interpretation of observational data. Vacuum chamber studies simulate the low-pressure conditions of interstellar space and their effects on material sublimation, chemical reactions, and structural stability over extended time periods relevant to interstellar travel. Cryogenic testing facilities reproduce the extremely low temperatures encountered in interstellar space, revealing how materials behave under conditions that cannot be achieved naturally on Earth, but are commonplace in the cosmic environment. Impact simulation studies investigate how micrometeorite bombardment during interstellar travel affects surface properties and internal structure, providing insights into the space weathering processes that modify these objects over geological timescales. The educational impact of 3I Atlas extends from elementary school astronomy lessons to graduate-level research seminars, providing concrete examples of cutting-edge scientific discoveries that make abstract concepts more engaging and accessible. Public planetarium shows and science museum exhibits featuring interstellar objects capture visitor imagination, while accurately conveying the scientific methods and discoveries associated with these cosmic wanderers. Online educational resources, including virtual observatory experiences, allow students and the general public to examine real observational data from 3I Atlas and other interstellar objects, promoting scientific literacy and engagement. Citizen science projects enable amateur astronomers and interested volunteers to contribute meaningful observations and analysis efforts, democratizing participation in interstellar object research while providing valuable data for professional scientists. The inspirational value of interstellar object discoveries motivates young people to pursue careers in science, technology, engineering, and mathematics by demonstrating that remarkable discoveries continue to emerge from systematic investigation of the natural world. Science communication efforts surrounding 3i Atlas help bridge the gap between specialized research and public understanding, translating complex scientific concepts into accessible narratives that convey both the excitement and rigor of modern astronomical research. The philosophical implications of studying authentic visitors from other stellar systems challenge anthropocentric perspectives and promote understanding of our planet's place within a vast, interconnected galactic ecosystem where material regularly exchanges between distant worlds. Environmental analogies help explain interstellar object research by comparing the galactic ecosystem to terrestrial environments where seeds, spores, and other biological materials travel between different habitats, facilitating the spread of life and genetic diversity. The timescales involved in interstellar object journeys dwarf human historical experience, providing perspective on the vastness of cosmic time and the patience required for understanding processes that operate over millions or billions of years. Cultural narratives incorporating interstellar objects appear in science fiction literature, films, and other creative works that explore themes of cosmic connectivity, alien contact, and humanity's relationship with the broader universe. The symbolic significance of interstellar visitors resonates with ancient human traditions of viewing comets and unusual celestial phenomena as omens or messengers, though modern scientific understanding replaces superstition with rational investigation. International cooperation in studying 3i Atlas demonstrates how shared scientific goals can transcend political boundaries and cultural differences, providing models for addressing other global challenges that require coordinated international responses. The technological challenges associated with interstellar object research drive innovation in multiple fields, including sensor design, data analysis, propulsion systems, and communication networks that benefit broader technological applications. Economic spin-offs from interstellar object research include advances in materials, science, computer algorithms, optical systems, and space technology that find applications in industries ranging from telecommunications to medical diagnostics. The strategic implications of improved capabilities for detecting and tracking small, fast-moving objects extend beyond scientific research to applications in planetary defense, space, situational awareness, and national security monitoring systems. Military interest in technologies developed for interstellar object research reflects their dual-use potential for tracking conventional threats, including hypersonic missiles, space debris, and other objects that pose risks to critical infrastructure and national security. The commercial potential of interstellar object intercept missions includes possibilities for recovering rare materials, demonstrating advanced propulsion technologies, and establishing capabilities for future interstellar exploration missions. Venture capital investment in companies developing interstellar object research technologies reflects growing recognition of their commercial potential and the expanding market for space-based services and exploration capabilities. The insurance industry analyzes risks and opportunities associated with interstellar object research missions, developing new models for covering the unique challenges and potential rewards of these unprecedented exploration efforts. Intellectual property considerations surrounding interstellar object research include patents on detection methods, analysis techniques, and potential intercept technologies that protect commercial interests while promoting continued innovation. The regulatory framework governing interstellar object research missions must balance scientific freedom with safety considerations, international law compliance, and planetary protection requirements that prevent contamination of Earth or other celestial bodies. Environmental impact assessments for major interstellar object research facilities consider their effects on local ecosystems, light pollution, radio interference, and other factors that might affect surrounding communities and natural habitats. The social responsibility of the scientific community includes ensuring that interstellar object research benefits all humanity rather than serving narrow interests, promoting equitable access to discoveries and their technological applications. Ethical considerations in interstellar object research encompass questions about resource allocation, research priorities, and the potential consequences of discovering evidence for extraterrestrial life or intelligence. The precautionary principle guides approaches to potentially hazardous aspects of interstellar object research, ensuring that safety considerations receive appropriate attention even when risks appear minimal based on current understanding. Transparency in interstellar object research promotes public trust and enables independent verification of results while balancing legitimate needs for protecting sensitive information and maintaining competitive advantages. The peer review process for interstellar object research faces unique challenges due to the rarity of these discoveries and the limited number of experts qualified to evaluate highly specialized analyses and interpretations. Scientific integrity standards for interstellar object research require exceptional rigor due to the high public interest and potential for misinterpretation of results, particularly regarding claims about extraterrestrial life or intelligence. The historical context of interstellar object discoveries places them within the broader narrative of astronomical exploration, from ancient observations of comets and meteors to modern space-based surveys and robotic missions. Technological evolution in astronomy enables discoveries that were impossible for previous generations, with interstellar objects representing achievements that depend on recent advances in detector sensitivity, computational power, and global coordination capabilities. The progression from ground-based visual observations to automated digital surveys illustrates how technological advancement revolutionizes scientific capabilities, enabling detection of phenomena that remained invisible to earlier instruments and methods. Future technological developments promise even more dramatic improvements in interstellar object research capabilities, including space-based telescopes, artificial intelligence systems, and potentially interstellar probe missions that could provide unprecedented detailed analysis. The miniaturization of scientific instruments enables deployment of sophisticated analytical capabilities on small spacecraft that could be launched rapidly to intercept newly discovered interstellar objects, providing close-up studies impossible through remote observation alone. Quantum sensing technologies offer possibilities for detecting extremely subtle signals from interstellar objects, potentially revealing magnetic fields, gravitational anomalies, or other properties invisible to conventional instruments. Artificial intelligence systems trained on vast databases of astronomical observations will enable automated discovery and classification of interstellar objects, reducing the time between detection and detailed characterization from weeks to hours or minutes. Biotechnology applications to interstellar object research include developing robust biological sensors that could detect signs of life or organic chemistry in return samples while minimizing contamination risks and false positive results. The convergence of multiple technological trends promises to revolutionize interstellar object research within the next few decades, potentially revealing a rich population of cosmic wanderers that dwarf current discoveries in both quantity and diversity. 3I Atlas represents more than just another astronomical discovery. It embodies humanity's growing capability to detect, track, and study authentic messengers from distant stellar neighborhoods, expanding our understanding of the galactic environment we inhabit. The scientific legacy of 3I Atlas will extend far beyond its individual properties to encompass its role in establishing interstellar object research as a legitimate field of astronomical investigation with its own methods, theories, and research communities. As 3I Atlas continues its journey away from our solar system, disappearing gradually into the cosmic darkness from which it came, It leaves behind a treasure trove of scientific data and a deeper appreciation for the interconnected nature of galactic evolution. The story of 3I Atlas ultimately represents humanity's quest to understand our place in the universe through careful observation, rigorous analysis, and collaborative investigation of phenomena that challenge our understanding and expand our perspective on cosmic processes. Future interstellar visitors will undoubtedly reveal new surprises and deepen our appreciation for the diversity of materials wandering through galactic space. But 3I Atlas will always hold the distinction of being among the first authentic extrasolar objects subjected to detailed scientific scrutiny. The knowledge gained from studying 3I Atlas contributes to humanity's growing understanding of planetary system formation, stellar evolution, galactic dynamics, and the potential for life throughout the universe, themes that define our species' intellectual journey toward cosmic awareness. In the vast timeline of galactic evolution, 3I Atlas represents just one moment in an ongoing story of material exchange between stellar systems, a process that has been occurring throughout the billions of years since the first stars began forming planets and ejecting debris into interstellar space. The detection and study of 3I Atlas demonstrates that despite the enormous scales and time periods involved in galactic processes, human ingenuity and technological capability can reveal the hidden connections that link distant worlds and provide insights into phenomena operating far beyond our direct experience. As we continue to develop more sophisticated methods for detecting and analyzing interstellar objects, 3I Atlas serves as a prototype for understanding how authentic samples from alien worlds can inform our knowledge of planetary formation, chemical evolution, and the conditions that might support life throughout the galaxy. The journey of 3I Atlas through our solar system represents a brief intersection between two cosmic narratives, its own billion-year wandering through galactic space, and humanity's recent emergence as a species capable of recognizing and studying such remarkable visitors from the stars. Looking toward the future, 3I Atlas inspires continued investment in the technological capabilities and international cooperation necessary to maximize the scientific return from studying these rare cosmic messengers whose brief visits provide irreplaceable windows into the nature and history of our galactic neighborhood. The legacy of 3I Atlas will ultimately be measured not just in the scientific papers it generates or the technical capabilities it helps develop, but in its contribution to humanity's evolving understanding of our place within a universe where distant stars regularly share their materials with neighboring stellar systems across the vast emptiness of space. Through careful study of 3I Atlas and future interstellar visitors, we participate in a form of cosmic archaeology, reconstructing the history and diversity of planetary systems throughout our region of the galaxy. Through analysis of the wandering fragments they have contributed to the interstellar medium. The story of 3I Atlas continues even as it departs our solar system, carrying with it the accumulated gravitational influences of our sun and planets while heading toward whatever cosmic encounters await it during the millions or billions of years of continued wandering that lie ahead in its future through the star-filled depths of galactic space.